pulse of light consisting of several photons into such a medium and then increase the, say, repulsive photon-photon interactions, then the photons may actually repel each other, so they avoid to overlap. And eventually, when you look at the output of such a medium, then the photons may, so to say, crystallize, meaning that the probability for finding two photons at the same time vanishes, and the intensity autocorrelation function is 0 for 0 time delay of detection, right? So if you want to achieve such a strong photon-photon interaction, then the conventional, let's say, approach is to strongly couple light with a quantum emitter and then make use of the inherently nonlinear response that such a quantum emitter has when interacting with photons in order to mediate the interaction between the photons. And this can be achieved, for example, by recycling the light many times in high finesse optical cavities where the quantum emitter is placed inside the mode of the cavity. It can also be achieved by mediating the photon-photon interaction via a strong interaction between Rydberg atoms, highly excited atoms. Or you can also place such an emitter into a tightly confining waveguide, so where the confinement is in the transverse direction, and where the light, so to say, cannot avoid to interact with the emitter, which is placed in the waveguide mode. And if you now want to enhance or further increase this interaction in order to enhance the control and fidelity of the operation, then what you have to do is to increase the light matter coupling strength on the one hand, and you should also reduce the dissipation because dissipation will make photons disappear and thereby blurs out the quantum nonlinear effects. And to increase this light matter coupling strength can be achieved by still more strongly transversely confining the light, for example, using photonic crystal waveguides as shown here. You can use resonators where the light is kept for a long time, so which feature high quality factors. And in order to reduce dissipation and reach high quality factors, you actually need low propagation loss, both in linear waveguides or in resonators. You need to lower the propagation loss, of course. And finally, you can also tailor your quantum emitter such that it features a strong dipole moment and thereby strongly couples to the light field. But even if you take all these approaches at the same time, it turns out that dissipation will always stay your worst enemy, because dissipation makes photons disappear and will just wash out all quantum nonlinear effects that you may want to observe or harvest. And the approach of the talk that I will be presenting is now to say, okay, if we cannot get finally or ultimately rid of dissipation, then if you cannot beat your enemy, so the dissipation, let's join your enemy. So make use of dissipation to achieve a quantum nonlinear interaction between photons. And the experimental platform that we use for doing these experiments is nanofiber-based atom light interface. So we use optical fiber, which we heat and pull such that it narrows down to a diameter, which is outer diameter, which is smaller than the wavelength of the guided light. And then we trap atoms along this nanofiber, which couple to the evanescent field, which protrudes beyond the surface of the fiber. And what we will see is that such a nanofiber-based atom light interface in the work I will be presenting here allows us to transform a flow of uncorrelated photons which come from a laser, so where the arrival times of the photons are completely random, into such an ordered flow of photons where the photons are anti-correlated, or we can also transform it into a bunched stream of light where the photons are correlated. Okay. So before going into the details of how this works, let me first explain how we trap atoms near the nanofiber, and then I'll go into the propagation of light through such a nanofiber coupled to an array of atoms. Okay, so the trapping is achieved using optical dipole forces, and we need two detuned light fields, one detuned to the red and one to the blue, to achieve stable trapping in the radial direction, because the atoms interact with the evanescent field outside of the fiber, which decays, or with an intensity that decays more or less exponentially. So an atom that approaches the fiber from a distance when the fiber guides red detuned light will be attracted towards the high intensity region, and thus would collide with the fiber. But then if at the same time we send blue detuned light to the fiber, then the blue detuned light is more tightly confined to the fiber because the decay length is proportional to the wavelength. The decay length of the evanescent field is proportional to the wavelength. And thus, when the atom approaches the fiber, it first sees the attractive red potential, or the potential induced by the red light, and is attracted towards the fiber. But then when it approaches the fiber further, it will start to see the repulsive potential induced by the blue light. And the sum of the two, can, choosing the detunings and powers adequately, can give rise to a potential which has a minimum at a distance of about 200 to 300 nanometers from the nanofiber surface. So that means that we can achieve radial confinement of the atoms. In our experiment, we actually need to control the position in all 3 dimensions. But this can then be achieved along the fiber. The confinement is achieved by sending a counter-propagating red detuned light field, such that we have a red detuned standing wave. So the attractive potential is modulated like a cosine squared along the fiber. And then we still have trapping in the radial direction, but in addition, there is also periodic trapping potential along the fiber, and the distance between 2 adjacent trapping sites is lambda half, so half the wavelength of the red detuned light in the fiber. So it's about half a micron in our case. And now, in order to confine the atom also in the azimuthal direction, so around the nanofiber, we take advantage of the fact that the light field outside of the fiber, or in general the fiber guided mode, for such a strongly guiding fiber with a high index contrast between glass and the surrounding air or vacuum, is actually polarization dependent. So when you send linearly polarized light into such ultra-thin fiber, then the evanescent field intensity in the plane of polarization is about 3 times higher than orthogonal to the plane of polarization. And this means that if we now use linearly polarized light for the red and blue trapping fields, which are orthogonally oriented, such that, for example, the blue light is horizontally polarized and the red light is vertically polarized, then there's more red detuned trapping light up here and more repulsive blue light here, so that we also get some azimuthal confinement. So if I plot the resulting trapping potential in 3 dimensions, then this is how it looks. So this is like a 400 nanometer diameter fiber with 2 diametral linear arrays of trapping minima. And here I plot equipotential surfaces 40 microkelvin and 125 microkelvin above the trapping minimum. So the distance from the fiber is about 200 to 300 nanometers. The trap frequencies are on the order of 100 kilohertz in all 3 dimensions, which means that the atoms are localized in all 3 dimensions to better than the wavelength, and we are operating the trap in the so-called Lamp-Dicke regime. So we were the first to realize such a 2-color nanofiber-based atom trap, but then others joined the game and realized or will realize atom fiber-based nanotraps. Okay. So now let us consider the propagation of light through such a nanofiber when atoms are coupled to the nanofiber guided light. Okay, and I should start this section with a disclaimer because Arne told me that Bill Phillips might join the seminar. I don't know if he has by now or didn't, but in any case, since Bill heard my talk, I did a very stupid thing. We talked this morning at around 10 or so, and I just changed my talk and have new slides. So this may mean that it's not quite as smooth, but I hope more pedagogical. And in any case, not what Bill saw the last time I saw the talk. He saw
sorry for hyping that up, but I think he didn't join. It's
okay. Anyways, so now I can't go back. You get that new talk. So the transmission through the nanofiber trapped atoms is just measured by sending a weak probe light now into our tapered optical fiber, which then via the evanescent field couples to the nanofiber-based atoms. And then we send this light onto a single photon counting module and look at the transmitted power as a function of detuning of this light field, okay? And if we now vary the detuning and measure the transmission of the light through the nanofiber, then we see that we actually deal with optically dense ensemble of atoms where the transmission here goes to virtually 0 over quite a range of a few 10 megahertz of detunings. And we can now look at the transmission at resonance. So for the laser resonant with the transition of our, for this theoretical considerations now 2-level atoms. And of course, what you expect for the transmission at resonance as a function of the number of atoms is an exponential decrease of the transmitted power, okay? So you expect that the transmission scales as e to the minus OD, where OD is the on-resonance optical depth of our ensemble. And this on-resonance optical depth of the ensemble is proportional to the number of atoms n, and the proportionality factor for beta here is given by the coupling strength of the atoms to the waveguide. And this typically is characterized in these systems as this beta parameter, where beta is actually given by the decay rate of the atom into the waveguide divided by the total decay rate, so the sum of the decay rate into free space and into the waveguide modes, okay? So that means that we expect an exponential decrease of the transmitted power as a function of the number of atoms, okay? So this is what is given here in the semi-log plot of the transmission versus the number of atoms for such a 1% coupling strength. So a 1% of the emission of the atoms is emitted into the waveguide. And you would then expect on a semi-log plot just this linear decrease or this linear dependency here of the transmission on OD. And actually, it turns out, and that was an insight that we got in 2018, that this is not what you should observe when sending light through the fiber if you look at it in detail. Because actually in 2018, Zahand Mahmoodian and co-workers studied the transport of photons through such an array of weakly coupled emitters along a waveguide, and actually found that for high optical depths, the transmission deviates from Beer-Lambert law and is significantly higher, and particularly it scales no longer exponentially for high numbers of atoms, but polynomially with 1 over the number of atoms to the power of 3/2. So this is really surprising, at least for me it was, that in 2000, I learned about it in 2019, a bag full of uncorrelated 2-level atoms still bears surprises to me, okay? And now let us try to understand what comes into play here. And for this, we have to consider the nonlinear photon transport, because linear transport will give rise to an exponential decay of the intensity along the fiber, okay? And so what we consider is a waveguide with atoms coupled along the waveguide on both sides of the fiber. The filling factor of our trap is not 100%. This is why there's some kind of random arrangement of atoms along the fiber, okay? And all of these atoms are now modeled as 2-level emitters, which may scatter the light that is sent through the fiber. We limit our discussion here to the low power case, or the weak resonant, so that the resonant drive field is actually considered as a superposition of 0, 1, and 2 photons. So it's a coherent state with a mean number of photons on the order of or less than 1, okay? So that we only have to now consider what happens to 1 and 2 photons propagating along the waveguide. And as I said, in our case, our beta factor is much less than 1. So this is also what is considered here. And another detail of the calculations, which simplifies the calculations, is that we will only consider a forward scattering, because it turns out that in our scenario, without going into the details, the atoms can only scatter the light into the forward direction. So meaning when the light comes from the left, then the atoms scatter the light, absorb it and scatter it to the right. But this is not a precondition for the scheme to work. It just simplifies calculations and the scheme, and it is realized in our experimental settings. But the scheme would also work if the scattering was symmetric. So if the atom could scatter forwards and backwards, okay? So the way that Zahan Mahmoudyan and co-workers treated this problem was using a scattering matrix formalism. So they just considered what every atom does to the light, and then summed up the contributions of all these atoms by multiplying the scattering matrices of the different processes here, okay? And when you then ask what comes out of the fiber, then there are actually 3 possible scattering processes which come into play. One is the simple 1 photon scattering. So an atom can absorb light from the fiber and scatter part of it outside of the fiber, and the remaining or other part of it into the fiber. And this scattering processes, if photons are arriving 1 by 1, is actually elastic, in the sense that the frequency of the scattered photons is not altered in this process. But then we also have 2 photon scattering, so that 2 photons interact with the atoms. So they arrive at the atom within the lifetime of the excited state. And in that case, the photons can actually exchange energy, okay? So the 2 photons which are monochromatic and come in will feature a broadened spectrum, where 1 photon can have slightly less energy and the other one slightly more energy. And energy conservation only requests that the total energy of the 2 photons is preserved in this scattering process. And then the third possible scattering process is, of course, when 2 photons arrive at the same time, then the atom may scatter 1 photon still out of the fiber. So we have 1 photon loss, which leads to a suppression of the 2 photon amplitude. And so all these 3 possible scattering processes take place for every atom. So if we then want to know the output, or this, then we, in order to get the scattering matrix of the ensemble of atoms, we just have to take these corresponding scattering matrices to the power of n. Okay, that correspond to these processes. So now let's go through these photon scattering mechanisms a bit more in detail. So when we look at single photon scattering, then this actually is, as I said, elastic in the sense that the atom does not change the energy of the photons, and it will lead to an exponential attenuation of the one photon component propagating along the fiber. So it's the transmission of one atom, the amplitude transmission of one atom to the power of 2n. So this depends again on the coupling strength of the atom to the waveguide. So this is just Beer-Lambert law as we would expect it. But then there is also the two photon scattering mechanism. And actually the two photon scattering has like two contributions, and the output state will then be given in this expression here, where we have creation operators for photons at position x1 and x2 as an integral over all positions x1 and x2, and the amplitude psi here depends on the position x1 and x2 of the two photons. And it turns out that since the problem is translation invariant, eventually this psi only depends on the difference between the coordinates of the two photons. Okay, so this amplitude here, psi, was now given by two contributions. One is the correlated photon pair that is generated in the scattering of two photons, where the two photons exchange energy. So here, this amplitude here depends on the distance or time between the arrival of the two photons at the atom, and this the spectrum corresponding to this process here will be a Lorentzian, which has a width which corresponds to the line width of the transition or to the decay rate of the excited state. In resonance fluorescence, just one mention here, in resonance fluorescence, this is what one usually calls the incoherent background of resonance fluorescence. You have the elastic component and then the so-called incoherent component. But what we see here is that this incoherent component actually consists of correlated photon pairs, which are time energy entangled, and where when I have one red detuned photon detected, there must also be a blue detuned photon more or less at the same time, so within the lifetime of the excited state of the atom, to preserve energy conservation. Okay, so this is the correlated part of this wave function here, and one can compute this. This is what was done here in the PRL by Mamoudian et al. I will not give the expression, but just say that this is the wave function of the correlated photon pairs. And then there is also just the probability for the two photons being transmitted past the atom without scattering. And this is just for a single atom transmission coefficient times the, to the power of 2n. Okay, so this is when the photon pair comes in and is just passes the atom, it remains uncorrelated. So here, an important part of this expression is this minus sign, okay? Because this means that there's actually destructive quantum interference that will take place. And where does this minus sign come from? It comes from the fact that here in this scattering process, which gives rise to the correlated photon pair, one photon is absorbed, then a second photon comes and stimulates the emission of the first photon. So in this process, there is absorption and emission of a photon, which then gives rise to a pi phase shift of the transmitted quantum state, okay? So this is this minus sign here as compared to the uncorrelated part, which is just transmitted. And this means that there is destructive quantum interference between the transmitted two-photon component and the scattered two-photon component, which is correlated. And in addition, the correlated part has a broader spectrum than the transmitted part, where the transmitted part is just the laser line width, it's the laser photons which did not interact with the atom, okay? So, and then finally, there's, of course, I mean, for this uncorrelated part here, there's one photon loss, which reduces this, so which gives rise to this finite transmission, because the two photons can arrive simultaneously at the atom. One photon is scattered out, and I'm left with one photon continuing in the fiber and one scattered into free space. And this contributes to an uncorrelated single photon background, okay? And now let us actually come to one of the consequences of this correlated photon pair here. The fact that this correlated photon pair has a broader spectrum than the laser, okay? It has a spectrum which is as broad as the atomic line width, implies that it suffers less loss than the resonant uncorrelated part, okay? So this part here is just damped exponentially, whereas here we filter a Lorentzian spectrum with a Lorentzian absorption of the remaining atoms, but this actually does not lead to an exponential decrease of the power. And after a while of propagation and interaction with atoms, this factor here will just go to 0, whereas this here, and it goes exponentially to 0, whereas this here only goes polynomially to 0 due to filtering. And this is actually what then gives rise to this deviation from the predicted deviation from Lambert law for high optical depth, okay? So it's the less efficient absorption of the correlated photon pairs when they propagate along the fiber, okay? Just
And the curve matches this polynomial decrease that they calculate?
Yes, yes. So actually, this here then goes down as n to the -3/2. So it's no longer a straight line in a semi-log plot. Yeah, exactly. Good. So then we can now look at the expected photon correlations that we should.
A quick question before
yes.
you go on. Can you explain the -3/2 power? Is there an easy way to see that?
Actually, my understanding is that if you, this is what comes out when you filter a Lorentzian spectrum with a Lorentzian notch filter. Okay. So you see, then the off-resonant optical depth is lower. And so when you propagate this spectrum through a filter and you look at the transmitted power and you increase the optical depth of your filtering Lorentzian, you do not decrease the transmitted power. So this has nothing to do with quantum mechanics. It's just filter a Lorentzian spectrum with a Lorentzian filter function. When you increase the OD, you get n to the -3/2.
It also means that what you get out after a certain number of atoms is correlated pairs.
So what you get out after a certain number of atoms is over proportionally many correlated pairs. Let me phrase it like that, because remember, there's also one photon loss. So also the correlated photon pairs, of course, will suffer one photon loss, which means that it would be more precise to say that for very large optical depths, all photons that you detect are remaining photons from a correlated photon pair. So one of the two photons may have gotten absorbed, but the other one still makes it through, okay? So you should not imagine the output as being photon pairs, because eventually you still suppress the transmission by filtering with a Lorentzian, okay? So if you go through very high OD, what comes out will be many more photon pairs than you would expect from Poissonian statistics. Okay, and that is something that we will see when looking now into the photon correlation function. Okay, yeah.
So more another question, and you guys can also put questions into the chat if there are.
Yes, please.
This Lorentzian filter is in the frequency domain, right? And
yes,
that means that the longer you make that depth, the further apart in frequency are those red and blue photons.
Absolutely, wonderful. Yes, this is what happens. Yeah, so you actually get like a seeming like side bands, but I wouldn't call it like that because it comes from filtering. Okay, so you filter a Lorentzian with a Lorentzian, then eventually you get two bumps to the left and the right of the detuning, and these bumps move outwards when you filter more and more, but they also get lower. Okay, that's exactly what happens. Mm-hmm. Okay, so now let's go to the photon correlations that we expect from the output that issues from the coherent superposition of this scattering mechanisms. Okay, and what we want to know is, okay, what is G2 as a function of time delay? And as I said, the time delay is equivalent to a physical distance between the photons divided by the group velocity. And if G2 for 0 time delay is then larger than for finite time delay, we speak about bunching, and when we have the G2 at 0 time delay smaller than for finite time delays, we would speak about anti-bunching. And what you can show is that this intensity autocorrelation function here is proportional to the modulus squared of this 2 photon amplitude that I introduced. Okay. So again, you can calculate this, but we will not. But remember that, or I could give the analytic expression here, but let us just remember that here we are dealing with an uncorrelated part, an amplitude that corresponds to the uncorrelated just transmitted to photon component, and the amplitude of the scattered component. And this goes down exponentially. And interestingly, this correlated part here initially increases with the number of atoms because there is actually constructive interference of the forward scattering of all atoms. So it's a collective scattering process. So initially, when the uncorrelated two photon amplitude is not too small, so nonlinear processes still take place, this increases and then will also decrease due to one photon absorption, but at a different scaling as 1 over n to the 3/2, whereas this goes down exponentially. And this means that at some point, these two amplitudes will become equal in, I mean, their modulus will be the same, but they have this minus sign here, and they will interfere in any case always destructively because of this minus sign. Okay. And this means that when we start with uncorrelated photons, so the G2 function of a laser, which is flat here, then after some propagation through our array of atoms, we have some correlated photon pairs and some uncorrelated photon pairs. They interfere destructively, but the amplitude of the correlated photon pairs is still much lower. So you expect slight anti-bunching because of this destructive interference. But if you then further propagate, then the uncorrelated part will be suppressed exponentially, whereas the correlated part is only suppressed like a power law, which means that at some critical optical depth or critical atom number, these two amplitudes will be the same, but due to the minus sign, they then interfere perfectly destructively, and you expect an intensity autocorrelation function which goes to 0 for 0 time delay. And then if you propagate the photons even further through the waveguide, or you have more atoms interacting with the photons, then the uncorrelated part here, so the initial laser photons, will be completely negligible, and we are only left with the correlated part. So this means that we now expect bunching appearing for 0 time delay corresponding to these correlated photons. Okay, and the spectrum, indeed, as you said, Arne, will then somewhat look like this. Okay, so I have the broad spectrum of the correlated photons, which is filtered by Lorentzian, and these two bumps here move outwards as I propagate through the fiber, and they are reduced in intensity. Okay. So if we then predict the value of G2 for 0 time delay as a function of the number of atoms here in a semi-log plot, then for very low optical depth, we just expect G2 of 1. But then for this then for all increasing atom numbers here, the value of G2 decreases because of this destructive interference and goes to 0 for a critical number of atoms here. And if we further increase the number of atoms, then this bunching occurs, and you expect that this actually diverges, and we get ever and ever increasing value of G2 for 0 time delay when increasing the optical depth. Okay, so this means that starting with a stream of uncorrelated photons, we can generate, using such a coupled array of atoms, anti-bunched or bunched light. Okay, and the parameter that we have to tune for going from anti-bunched to bunched is the number of atoms, or the OD of the ensemble. Okay, so just a few words about the actual experimental setup. So our tapered optical fiber confines the light to, the diameter is 400 nanometers, and the wavelength of the probe is 852 nanometers, because we're dealing with cesium atoms and talk to the D2 line. This means that the light is transversely confined at the wavelength scale, and there's very efficient light matter coupling or atom light coupling. The tapered fiber allows us to adiabatically transform the fiber guided mode of the standard step index fiber here into the nano fiber guided mode and back with typically better than 99% transmission. And one important aspect is that the fiber fluorescence, which is induced by the trapping light fields. Remember, we have here milliwatts of trapping light, which is blue detuned with respect to the atomic transition frequency, and this causes fluorescence. But this fiber fluorescence is low enough so that it can be actually suppressed with bandpass filters, such that when then analyzing the photons here with a Hanbury-Brown twist setup, we're sure that the photons we detect are actually have issued from the laser and or the interaction with the atoms, and not from some spurious generation by Raman processes in the fiber. So the probe light that we send here is resonant with the D2 line transition of cesium, and the input power is a few picowatts, which means that the saturation parameter of the light seen by the first atom along the nanofiber is 0.02. So we are indeed working in the low saturation regime, where you would probably not expect too much nonlinear effects taking place. And indeed, for every single atom along the fiber, the nonlinearity is minute. However, in the forward scattering, there is a collective enhancement of this nonlinearity, because all amplitudes of the correlated photons that are sent forward add up constructively, and this is what gives rise to a sizable nonlinearity of the ensemble. For the experts, the probe light that we send in here is quasi-linearly polarized, so we launch linearly polarized light into the fiber, and this is what gives rise to this chiral or direction-dependent atom light coupling, where the atoms only scatter light forward. But as I said, this is not a prerequisite for the scheme to work. So here, then I show you the experimentally measured second order correlation functions, G2 as a function of time delay for a varying number of atoms. This is the mean number of atoms along the fiber, varying from 100 to 200 roundabout. And the blue line is the experimental data, and this red line is the theory prediction. And actually the numbers of atoms that I show you here from 100 to 200 correspond to optical depth ranging about from 3 for this measurement here to about 7 here. And what you clearly see is that there is indeed some anti-bunching here, which gets more pronounced. I should stress that here we changed the scale. So while here G2 is plotted from 0 to 2, here it's plotted from 0 to 10. And you see here some onset of bunching, as Anders Sørensen said, with the eyes of a loving feather. But here, actually, for even higher optical depths, you clearly see some bunching for 0 time delay. Okay, and yes.
Is this like, I mean, just wondering about the experimental setup. Can you do this with the same configuration of atoms along the optical fiber? So it's not that you have like several shots where you load your trap and then you have basically a stochastically fluctuating atom occupation.
So you're pointing to something that will be issue of the next sentences that I show on the slide, exactly, which is actually that we are not able to prepare a precise number of atoms, but we load the atoms from a magneto-optical trap into our nanofiber-based atom trap. And this means that even if everything was perfectly stable, we would still have Poisson fluctuation of the atom number. And it turns out that our fluctuations are somewhat larger even than Poisson due to technical fluctuations. And this orange line here, which is the theory prediction, takes this fluctuation into account, because what we do in order to determine the optical depth or number of atoms is to measure the transmission through this sample. Okay, so in the beginning of the sequence, we measure how many atoms we have by sending light through the fiber and looking at the transmission. However, also for the high optical depths that we deal with, the transmission is so low that we are starting to count photons in the transmission. So also there we have Poissonian fluctuations, which give rise to an uncertainty of the optical depth that we actually have. Okay, and in addition, in order to have sufficient statistics, we also have to bin the optical depth. We have to say, okay, let's look at the data for optical depth ranging from 5 to 5.5 and so on. Okay, and this gives rise to some variation in the atom number distribution, and this then gives rise to some washing out of the features that we want to see here. Okay. But in any case, even in the presence of this atom number fluctuations and post-selection of samples with a given atom number, we are able to see the effects, the main effects of the physics we're interested in. Actually, for this red theory line here, this is not a fit, but it's actually just assuming an atom waveguide coupling strength, and this atom waveguide coupling strength of about 1% is derived from the value of G2 at 0 time delay that we measured as a function of OD, and there we fit this with beta as the only fit parameter. And as I said, we clearly see bunching and anti-bunching. Let me show you this fit here of the G2 of 0 time delay versus the optical depth. So this is our data, the blue dots here. And then when fitting this G2 versus OD, with varying beta and taking into account the fluctuations of the atom number, then the red line is our prediction. For comparison, I show the ideal case. This is this green line here, which we should observe if we were not having fluctuations of the atom number. Then for the critical optical depth here, you would expect 0. In our case, it goes down to 0.4, the strongest anti-bunching we measured. And of course, you see a transition here to bunching for about 180 atoms, but to see the bunching, we then have to go to this is a linear scale, we have to go to a log scale. So this is what you see here. So on a log scale, we can also show that we actually observed here for higher optical depths going up to 8, bunching with G2 values of about 20. Okay, so this was the largest bunching we could observe, and the transition from anti-bunching to bunching takes place at about 180 atoms. Okay, so let me summarize. This means that an ensemble of weakly coupled atoms can still be used to realize a strongly correlated many-body states of photons, so an effective photon-photon interaction, where the underlying dynamics is actually based on an interplay of a weak optical nonlinearity of every atom, which is collectively enhanced because all atoms scatter in the forward direction. And we also need the finite dissipation, because this suppresses the uncorrelated photon pairs and allows us, due to the different scaling of the correlated and uncorrelated photon pairs, to have this point of critical optical depth where you expect perfect anti-bunching. Where can all this lead to? So, of course, we know, in atomic physics, one knows that a weak coupling can be like collectively enhanced, right? So this is used in whatever cavity quantum electrodynamics by coupling an ensemble of atoms to a cavity. But here, to our knowledge, this is the first time that a collective enhancement was used to actually enhance a non-Gaussian operation, where you transform the laser light into such a non-Gaussian state, which is anti-bunched light. Okay, and we think that this significantly broadens the possible applications of our scheme. In particular, for example, in quantum information science, you can use this to realize a fundamentally new approach to realizing a single photon source. So here this realizes a stream of anti-bunched photons, and interestingly, it does not depend on the type of emitter or the coupling strength. So and it doesn't depend on the frequency or spectral range. So in principle, this scheme would also work for realizing anti-bunched X-ray photons with very weakly coupled nuclear transitions in atoms, just as an example. Okay, so we think that this may be superior in regimes where no strongly coupled emitters are available. Okay, of course, if you have a strongly coupled ion coupled to a cavity, then you use this as a source of single photons. But in spectral ranges where you don't have such a strongly coupled emitter available, this scheme may be of interest. So with this, I would like to thank the funding agencies, and I would like to thank you for your attention. And if you want to read more about it, then this work was recently published in Nature Photonics. Thank you very much.
Thanks for the great talk. Very interesting stuff.
Yeah.
I'm sure
I have a question.
I have questions.
Yeah. You have told that one can really realize a kind of single photon source.
Mm-hmm.
And for that, you would need an anti-bunching, and probably then you are in the regime of sub-Bosonian somehow.
Yes, so such an ideal probabilistic single photon source should have G2 of 0 for 0 time delay.
Yeah, but then you need less atoms in the trap. Is that correct?
No, you need the number. The number of atoms that you need is the critical number of atoms. In our case, 160, where the correlated photon pairs have the same amplitude as the uncorrelated photon pairs, which remain from the laser, and such that they interfere destructively. Okay, so this is not an effect which comes from a single atom, but it's actually an collective effect of an ensemble of atoms that transforms light from a laser into a stream of anti-bunched photons.
And have you been able to produce single photon source, or just a perspective for the future?
So, I mean, if you like, then this here is the demonstration of a bad single photon source. I mean, we transformed the stream of photons into one with a G2 of 0.4. Of course, for a good single photon source, this point should be down here.
Yes.
However, remember that this here is limited currently by the atom number fluctuation. So if you wanted to use this as a practical single photon source, then, for example, you should use either, you could use ions and count them, and you know how many ions you have, and couple them to your waveguide. But you could also use, for example, solid state emitters coupled to a waveguide, where you just by construction know the number of solid state emitters, right? And you just place the right number of emitters with the right coupling strength to the waveguide, and out comes a stream of perfectly anti-bunched photons.
Okay.
Mm-hmm.
Thank you.
Maybe I can add a stupid question, probably, because I'm not super familiar with G2s. What does a G2 of 20 mean? Does it mean that you have 20 photons coming?
No. Yeah. This is a very good question, because this is very important. And I was honest, and I try to be as honest as possible. I started by explaining what comes out of this source. And maybe when you see G2 of 0 of 20, you think that you only have pairs coming out of the source, okay? But a G2 of 20 means that the probability for having a pair is 20 times as high as in the case of Poissonian statistics. When you look at the rate of single photons compared to two photons, then this ratio is fixed by this G2, okay, of 20. But of course, when you decrease the power, then eventually your stream almost exclusively consists of single photons. And if you have a very low flux of single photons, then one pair per year would still give you a large G2 of 0, you see? So the question is, what is actually the output flux that you get? This is another question that you have to ask here. And it turns out that for the point of, so that this source here would not be a good pair source, because you don't get a lot of pairs out because of this absorption that still takes place. But when you look at the output flux of anticorrelated photons, so at the point of 0, G2 of 0, then the output flux can be like almost 1/2 of the maximum value that you can get from a single perfectly coupled emitter, okay? And remember, I think it would be fair to compare this scheme here rather with, if I have, say, an emitter which has a coupling strength of 1% to the waveguide, how many single photons can I get from a single emitter that I excite, and I collect with this 1% collection efficiency the photons? Then I get a flux. And in this case, we are orders of magnitude better by putting the same emitter with the same coupling strength many times along the waveguide and absorbing the light that goes through the waveguide. So that's the message, okay? But it's a very good question, and very important to note that G2 of 0 of 20 does not mean that you're dealing with a flux of pairs, but you're dealing with a flux that has many more pairs than expected from Poissonian statistics. Okay.
Are there more questions? You can also put questions in the chat if you're too shy, then I can read them for you. But Adima wanted to ask a specific question about something I forgot.
I already asked it. I can't wait till the end, so I already asked it.
No, but I mean, there was something else, no? What did he say?
I said that, okay, so Arno explains the modes in this fiber like nobody else. You know, once you see how he does this, you can never forget it in your life. That's what I
Thank you.
Yeah.
Thank you so much.
I'm referring to the Travolta mode, you know, in the fiber, of course. If you remember, Arno.
Yeah. We had some discussions on the wild polarization properties of these modes.
Yeah.
I have maybe a stupid question. How do you control the thickness of these fibers during the production process?
Yeah, this is actually so this was the issue, and we need a way of making fibers with a known thickness without having to measure it. So this is not a post-selection. We don't make a fiber, measure the diameter, and then use it, because the ways that would be at hand to measure the fiber diameter would spoil the fiber. And it's actually done by modeling the fiber pulling process. So we have a very stable translation stages that stretch the fiber, which are computer controlled. And we have a very stable flame that heats the fiber and has a constant width. And then it turns out that the modeling is only using one underlying principle, which is volume conservation, because the glass gets soft, but it doesn't evaporate. So that means that when stretching the fiber while brushing with the flame over the fiber, you can calculate what comes out. And it turns out that our modeling of this process gives us like an a priori precision of the final fiber diameter, which is better than plus minus 5%. Okay, so over 3 orders of magnitude of reduction of the fiber diameter. So we start with 125 micron diameter fiber, we go down to 125 nanometers, and we meet this 125 nanometers to within plus minus 6 nanometers. And this is just by modeling the process and then doing what the computer calculates what has to be done to achieve a certain radius profile of the fiber, and the outcome matches the predicted profile to better than 5%.
So when does the transmission go to 0 of those fibers as a function of diameter?
When the diameter is a quarter of the wavelength. So you actually hit a kind of hard wall where so we have just recently, together with Offa Fürstenberg, worked with atomic vapors and wanted to have the largest possible mode, and we could actually realize tapered fibers with, I think it was 150 nanometer diameter for rubidium light. And there, just to give you the ratio, so the ratio between the evanescent field, the optical power guided in the form of the evanescent field outside of the fiber, and the optical power inside the fiber is like 98% is evanescent field and 2% is still in the fiber. So almost 100% of the light is outside of the fiber, and it's a huge mode that extends over like 13 wavelengths or so away from the fiber. But then actually you further reduce a tiny bit and the mode explodes, and you have like a 1 meter mode which doesn't know that the fiber is anymore there. I mean, theoretically, of course, the fiber always guides the light, but it becomes impossible to adiabatically match the mode from the taper into this nanofiber section. There's some double exponential scaling of the length of the taper that you would need to do this mode matching, and then you all of a sudden need a 1 kilometer taper to get light into the fiber, which is not practical anymore. So there's some chat message.
I don't have chat messages. Or do I?
Okay, no, it's a private chat message. Okay.
Maybe like, since you mentioned it, well, I'm not answering my own question. The question is whether this filling factor matters, right? I mean, you have still like a stochastic occupation of your little wells or your traps.
Mm-hmm.
And would it make sense if you consider an application to go into a field where you have like deterministic occupation numbers
Yes, yes, definitely.
Cold
So I
atoms.
mean, first of all, for the scheme I show here, the filling factor does not matter, because we are dealing with like a interference where you could say, okay, but then filling factor may matter, but it turns out that it's interference in the forward direction. And interference in the forward direction when you go through some random medium is always constructive. Okay, so no matter if the distance between the, so it doesn't even matter whether our atoms are periodically arranged, you know, so they only have to be arranged along the fiber, and then all of the forward scattering will always interfere constructively. However, yes?
I'm just like, really?
You say really? Yes.
Yeah, what about Bragg mirrors and this kind of stuff? I mean,
but this is for back reflection.
Yeah, but I mean, that also means that the transmission goes to 0.
Sure, but in our case, we don't have it. I mean, you would actually, if you had a periodic arrangement which meets the Bragg condition, then you have other effects which may even be a problem for the scheme here, because you may get collective enhancement of the back reflection. Okay.
Mm-hmm.
However, I mean, the periodicity of our trapping arrays is incommensurate with the resonant wavelengths. I mean, we induce the trapping potential with a wavelength which is 100 nanometers detuned from the resonance. Okay, so it's incommensurate, and we don't need, and there's no difference between an incommensurate periodic arrangement or a completely random arrangement for the effect we're seeing. So that is what I wanted to say. You're completely right, that when arranging the atoms in a Bragg condition, then you can actually get back reflection, enhanced back reflection. Okay. And but you're absolutely right about the unity filling. That would be very exciting, and we have now a Marie Curie project starting to and where we want to achieve this. Because if we were able to have unity filling and the atoms closer together than lambda half, then it turns out that the atoms cannot scatter light into free space anymore. So you actually get selective radiance where the state that is like the excitation of the atoms gives rise to a state which does not radiate into free space, but only into the fiber. There's destructive interference for all directions of free space. And in this case, it has been predicted by Derek Shang and co-workers that the efficiency of quantum memories no longer scales exponentially with the optical depth, but that the scaling, I mean, that you have an exponential gain in the scaling of the fidelity of the quantum memory with optical depth. So all the calculations for the fidelity of quantum memories with optical depth assume that there is actually uncorrelated emission into free space. But if you have such an array of atoms along a waveguide where the spacing is smaller and the filling factor is unity, then you expect a much better scaling of quantum fidelity of quantum memories. So there's one application.
Well, thanks. It sounds like a much more complicated experiment, though.
Well, I mean, we realized the quantum memory a while ago with these atoms on the fiber. However, with such a larger spacing and random filling. In principle, we would have to do that experiment again, just with unity filling factor. And that is indeed complicated because you need a complex loading scheme that makes sure that there's exactly one atom per potential well.
Mm-hmm. May I?
Mm-hmm.
I wonder if dynamics of light atom interactions in such a system is an interesting problem. Also, I guess it's relevant for memories potentially, because how you, for instance, store a pulse in this or things like this, right?
Absolutely. So, I mean, we're right now working on an experiment, or have data also already, where we are sending a pulse into the ensemble and look at the transmitted signal when you send just a boxcar-shaped pulse into the ensemble, and then you see the dynamics of the system, and you see what other groups have termed free space vacuum Rabi frequency. So you actually see that the transmitted light exhibits oscillations which come from onset of collective Rabi oscillations, where this Rabi frequency scales with the square root of the optical depth, so the square root of the number of atoms. So you see that it's actually a collective Rabi oscillation of the ensemble that is driven by this pulse. And also when you switch off the pulse, there is a decay which initially scales quadratically with the number of atoms. So there's like a so-called super flash of light. Some people call this super flash, where the emission from all atoms is much faster than a single atom. And then for very high optical depth, you also see such Rabi oscillations in the emission. So we're looking into this. This is I find this a very interesting and intriguing situation, because you actually can link cavity quantum electrodynamics with free space atom-light interaction. You can make a continuous transition and you can link all quantities between them, and you do see a vacuum Rabi frequency in free space, actually.
Amazing.
There's a question in the chat. Can you perhaps explain once more how you control the number of atoms along the fiber?
Yeah. So to start with, the rough number of atoms, actually, when we want to work with high optical depth, we need to do many more experiments to have enough statistics. And for the low optical depth, we don't need to do so many experiments. So what we do is we roughly set the number of atoms by like the keeping the atoms for a while, and then we just lose them over time. Okay, so this is how we roughly know. I mean, once we load the atoms, we can wait a while and we have less atoms, or we can do the experiment immediately. So this is how we set roughly the OD. And then for every experiment, for every experimental sequence, in the beginning of the sequence, we send a resonant light pulse onto the atoms, which is very weak, and where we look at the transmission, and we just measure the transmission of the ensemble by looking at the transmitted power and then relating that to the transmitted power without atoms. Okay, and from this we deduce the optical depth. That's it. So we just look at transmission and know the optical depth. The problem with this is that for high optical depths, and this is what you see here in the error bars, the number of transmitted photons then can be counted on with your fingers, you know, and then you have Poissonian noise on the number of transmitted photons, and then calculating back from this transmission of 7 photons to the OD, you get Poissonian noise on the determined OD. And this is why for large ODs here, we get larger error bars on the horizontal axis. So this is what washes out our signal somewhat. You know.
Great, thanks. Are there more questions? Oh yeah, good. Can you please explain what exactly is happening in the 2-photon scattering case? How we end up with photons of different frequencies?
So I have let me just switch to that slide. I think I have to, can I, yes, this way. I have a slide where I explain this here. So in resonance fluorescence, when you send in laser light, as I said, then if the photons arrive one by one, then energy conservation tells you the scattered photon has to have the same spectral power density as the incoming light. But if I now have finite saturation, and you always have finite saturation, it's not zero intensity, then there's some probability for 2 photons, which are indicated by this brown arrows here, arriving at the atom within the lifetime of the excited state. Okay, so this is what we will then call simultaneously arriving photons, or that they arrive at the same time. So they only have to arrive within the lifetime of the excited state. And in this case, what happens is a 4-photon process, which is somewhat similar to 4-wave mixing in a sense, you see. So you actually absorb 1 photon, then you emit a red detuned photon, and before like the atom has time to notice that it violated energy conservation, it absorbs a second of these 2 incoming photons and emits a blue detuned photon. So this is a 4-photon process where 2 pump photons disappear and 2 new photons appear. And this is actually permitted within the lifetime of the excited state, meaning that the energy width of these 2 photons can be equal to the energy width of this excited level here. Okay, and this is why when we look at this
permitted, I would guess it's also permitted much further away, just with this probability.
Yeah. I mean, this is a Lorentzian spectrum. So you're absolutely right. So this is actually, it has to happen, when I say it has to happen within the line width, then actually the true distribution, this is what I try to indicate here, of the frequencies of these 2 photons is given by a Lorentzian, which is just the Lorentzian of the atomic transition line. So you're right that you can have very large detunings of these 2 photons, but with much lower probability. But the Lorentzian goes to infinite detunings in principle. And that means that the scattered, the spectrum of the scattered light here then has this elastic component, but in addition, this incoherent background, which is actually, when you read Koh-Tanuji, then this is what is called incoherent emission or incoherent background. But this incoherent background is not really incoherent for the in the sense that it consists of correlated photon pairs. So if I detect a photon, say here, do you see my mouse actually? Yeah, if I detect a photon at this frequency, there must be within the next lifetime of the atom, say, a blue photon on that side, okay, with exactly the negative detuning. So this is inevitable, okay? And this means that while you call that incoherent, it's only incoherent when you look at single photons, okay? But the single photons are part of photon pairs, and the emission of the photon pairs is a coherent process. All right, so this here is a coherent 4-photon process. And this is also why the amplitude of this process can interfere constructively in the forward direction and can be collectively enhanced.
Great. It's already like 3:30, so we are like pretty long, but there is another question. So I'm sorry.
I'm
this keeps
very
on
happy
going.
about it.
Okay, that's from the same person. Then it is 2 photons interacting with the same atom in a very short time and not actually a photon-photon interaction. Oh, well.
Can you let me read that question again? Can you please explain what it's exactly having and so forth? Then it is 2 photons interacting with the same atom in a very short time and not actually a photon-photon interaction. Well, not exactly. I would still, so what really happens is you redistribute photons. So in that sense, it's a photon-photon interaction, because look, if 2 photons arrive with a certain time delay, there's 1 photon arriving a bit earlier and the other one a bit later, then this photon will be absorbed by the atom. And then the second one stimulates emission. And this I would call stimulated emission, a photon-photon interaction. And then both photons leave simultaneously. So the atom is a kind of delay line for the photons. Okay, so when it absorbs a photon, it keeps it for a time of a few 10 nanoseconds. And during this time, if a second photon comes, it stimulates emission. Okay. And in that sense, if you would agree that stimulated emission is a photon-photon interaction, okay, mediated by the atom, of course. I mean, it's all that is always mediated by the medium. It's nonlinear optics. Then, yeah, then I would still claim it's photon-photon interactions.
Great. Okay, so maybe it stops now with the questions. Anyway, I have recorded the whole talk, and I did it already last week. If you would be okay with that, if I can upload it to YouTube.
I'm very happy about it. Thank you.
Cool. And then maybe I give an advertisement for next week's seminar, which is given by Tracy Nossap from Rainer Blatz Group in Innsbruck. So she's probably well known to everybody in the ion trapping community here in Mainz. She's going to be talking about trapped ion interface for quantum networks. And then maybe, okay, if there are no further questions, Arno, I really, I mean, thanks a lot for your nice talk. It was great. It was very interesting.
Thank you for inviting me.
Thanks so much.
And thanks also for the great discussion.
Yeah, that was awesome. Yeah, I mean, we had a good discussion. Thanks for that.
Cool. I think we can just like, I will leave it open. The channel will disappear in 9 minutes. But yeah, so official program is over. So if you guys want to hang around, then
okay. So okay. I have to excuse myself, I'm afraid, because outside people are waiting for me. But thanks again, and take care.
Thank you very much.
Thanks a lot.
Thanks.
Bye.
Bye.